Good evening, everybody. Thank you for being here. Don't know that anybody else is going to be showing up, so I guess we'll get it started. My name is Stephen Hensley, and today I'll be giving you a not very brief, but hopefully very informational and enjoyable presentation on analog synthesizer design and what I've specifically been doing for it and gotten out of it. So a little bit of background about myself. My name is Stephen Hensley. Nice to meet you. I am a dual degree student in mechanical engineering and musical audio engineering here at UA. I'm in my last semester and I will be graduating in December. And I have played piano classically for about 12, 13 years and have gotten into synthesizers and keyboard sound design and all that fun jazz only about 4 years ago. And I've been really finding it enriching and enjoying it myself. And I've also been very fortunate to have some experience as a touring keyboardist and a studio musician, which has been wonderful. So that's a little bit about myself. So now before we get into the meat and potatoes, let's get into the ingredients. Let's talk a little bit about general information about synthesizers and why I am designing one for myself. So a synthesizer is electronically is a set of electronic circuits that generates and manipulates an audio signal, and that can be in any way, shape, or form. So that could be anything from a general oscillator to a sample-based digital synthesizer. And so there are several synthesis methods. Too many to list here. I'll just list off a couple. Subtractive is the, I guess, primary and probably the most popular. It's the one that I am pursuing in this project, and that includes removing harmonic information from a basic sound to get more complex wave sounds. Additive synthesis is the opposite of that, where you are adding harmonic sine wave frequencies to make more complex sounds. Frequency modulation is using audio rate sine waves to modulate other audio rate sine waves to make ridiculous, crazy sounds, and that became relatively popular in the 80s, if you're familiar with the DX7 and all the synthesizers that spawned off of that. And wavetable synthesis, which is very, very complex, and it's relatively recent within the past couple decades. And that is a three-dimensional map, a topographical plane that you then choose a cross-section of, and you can sweep between cross-sections of to make really dynamic, complex sounds. And so, as I said before, I am pursuing a subtractive synthesizer since that is the palette, the tonality that I enjoy. So also let's talk about voice count before we move on to anything else. Polyphonic synthesizer is a single voice synthesizer, so that is, you can only play one note at a time. You play another note, it moves to that note, that's it. And a polyphonic synthesizer has multiple voices, so you can play up to 5, 10, 15, 20, as many as the instrument itself allows, and once you reach that limit, then it starts stealing other voices to play new notes. So the construction of a very basic subtractive synthesizer voice is your oscillator, which just creates a wave. It does nothing else but creates just one constant running wave. And that wave is controlled by a pitch control and is run into a filter, which then cuts off harmonic information, either highs, lows, mids, whatever that filter specifically does. And that is often controlled by a cutoff control. And then you have your amplifier stage, which is your loudness. So instead of having the sound on all the time, the amplifier controls when it turns on and off, often in conjunction with a keyboard instrument or some controller like that. So that is your very basic synthesizer, subtractive synthesizer voice. But getting a bit more complex, you'll find any myriad of numbers of layouts or schematics or anything like that for voice design. This, for example, is sort of like the mini mode, where you have several oscillators into a mixer, which passes into a filter, which is then controlled by an envelope generator and a cutoff control, and then modulation waves, and is sent to an amplifier, which is controlled by its own set of cutoff envelopes and waves and all that before it gets sent out to the output that you hear. Now there is a very much flexible manner of synthesis called modular synthesis, where you pick and choose specific modules that you'd like based on your desires and your tastes. So you can choose one general oscillator and one general filter, and then you can choose some incredibly complex digital signal generator and then a really weird wave folder and all that sort of stuff to put it together into what you like. And the reason I bring this up for you today is because the DIY scene for modular synthesis is extremely large, and it's been going on for decades now. And so there's a massive wealth of information online about creating your own modules and all sorts of circuit schematics and blogs and all sorts of information that you can pull from and that I have pulled from to design your own circuits and move forward with your own design. And these all sort of adhere generally to the Eurorack format of voltages. It's a standard that defines power as plus minus 12 volts, maybe plus 5 volts. It defines your output waveforms as probably plus or minus 10 volts peak to peak. So it's that sort of standardized system that ties everything together. And so a lot of what you're going to see from me also happens to fall into that because of where I've taken my schematics from. So why do any of this at all? It's because I am a dork and I like synthesizers. And unfortunately, them being relatively high precision instruments, they're expensive, which is a shame, and I don't have synthesizer money to just throw around right now. But what I do have is mental capacity that I can toss around at making my own. So this way I can save the money, at least some money, from buying a market synthesizer that I might not even like all the features of. And I can have, cherry-picked features that I really enjoy and that are important to me all in this synthesizer. And then this is also really just a great way to learn about electronics and pick up new information, learn about new components that I might not have known about otherwise. So the objectives for this project laid out here: create an analog subtractive synthesizer for myself using as many discrete components as I can and avoiding using specialized integrated circuits. So these are like black boxes that'll just do a function that it's already designed to do, like an oscillator IC or a filter IC. I'd like to avoid that so I can actually learn how these things work and get a handle on these discrete components. I would like to be polyphonic. That's big for me just because I don't have a polyphonic analog synthesizer. And I'd like to be able to store presets, which is also really important in a live context. You can't go waiting a minute or two between songs, twiddling knobs to get a new sound for that next song, or even in the middle of a song. So preset storage is very important as well. I'd like it ultimately to be bitimbral, so I can split either across the keyboard one sound left, one sound right, or have two distinct sounds layered on top of each other. And I'd also like it to have MIDI and control voltage implementation, so it can take in MIDI signals or it can take in raw voltages to control the notes and the actions that it's generating. But for now, for this first iteration of my synthesizer, I'm just going to make a monophonic prototype, one voice, to get the taste for, taking one thing from start to finish before I really jump into the deep end and get out there with crazy voice counts and giant manufacturing processes and all that. So the main aspects of this project are analog circuitry design, and so as I mentioned before, primarily discrete components. And unfortunately, well, not unfortunately, this is really cool, but unfortunately for what I had done the last time I gave this presentation, every single thing, every single parameter that I'd like to control for this synthesizer must be voltage controllable because I want to store presets. So I can't have a potentiometer or a switch, an analog switch, built into a circuit because that won't change with the push of a button or a turn of a preset knob instantaneously. That is a reliance on a set fixed analog device. That can't have that on a preset synthesizer. So that brings us to our digital control processing. So this is going to involve analog control voltages from a control panel taken into a digital buffer, which is a controller that can, store and load presets and process all this information, and then out to analog sound generation circuitry so that you have that lovely analog sound. And so this includes both hardware design for all the circuits and software design for processing all this data. And once I have all these circuits designed and I'm happy with how they operate, then I can move on to PCB design, which is a printed circuit board, which is a tangible piece of, I couldn't even tell you what they're all made out of different things, but essentially they have electronic traces built inside, and you can install all your components onto this circuit board to make a fixed component, or a fixed circuit that you can then interface with other circuits, instead of having to constantly breadboard things and all that. And then I will also have to design the front control panel for, reasonable humans to understand how the thing works, which also includes the, behind the scenes of all the control voltages and how that's all getting passed around to where and when and all that, as well as the case design, but that is the very, very last step, and I'm not thinking about that right now. So as of the last presentation, I had a completed power design PCB, which I, still have and have been using when testing this circuit at home, and I'm using it here in the setup today. I had an operational oscillator mixer, envelope generator circuit, and also an OK filter that wasn't super reliable. The unfortunate reality was that these were all completely analog circuits for the most part, and that I either had to switch out a lot of the circuitry to make it voltage controllable, or just ditch the circuits entirely, which we'll get to in a minute. So still to do, as I just mentioned, was control voltage implementation for all these circuits, as well as the digital control system, which is what I really spent a lot of time on this semester. And then I still have a lot of analog circuitry that I'd like to get to down the line, including things like effects and stuff that'll be at the end of a signal chain. And then PCB design when that time comes for each individual circuit. So I'll try to keep this as short as I can, dig into the analog circuitry, but this is going to take a little while. So let's very first briefly talk about the voltage control of analog circuits. As I had mentioned before, analog circuits are often controlled by human manipulation devices, so that are potentiometers, switches, things like that, that are in a physical state set by a person, and that sit in that state until a person changes it. So these aren't, voltage controllable. And unfortunately, a lot of these circuits that you pull from these DIY Eurorack scene online are very much analog circuits, because you're not storing presets with modular synthesizers. It's extremely difficult to do. So I had a lot of that kind of circuitry that I've had to switch over. And so that includes overhauling circuits or switching parts out. And I would like to give a brief mention to the OTA, the Operational Transconductance Amplifier. This is a circuit component that I had never heard of until I was researching this audio sort of gear. I was looking at a lot of schematics for vintage analog synthesizers that stored presets and had all this voltage control, stuff like the Prophet 5 or the Polymoog, stuff like that. And I kept running into this components in all these schematics, and I had absolutely no idea what it was. It sort of baffled me, but I could identify it as almost an amplifier, voltage-controlled amplifier. And so after doing a lot of research, I found that this kind of falls under the operational amplifier umbrella. For those of you who are familiar with electronics, this component measures the voltage difference across its two input terminals and spits out a output current proportional sort of to that input voltage. But what's special about the operational transconductance amplifier, or OTA, is that you can provide it with a bias current that determines how much gain or how much transconductance, which is amperage divided by voltage, how much transconductance is applied to the input voltage difference. So if you have a bias current of 0, it'll not amplify at all, it'll just spit out nothing. And then if you feed it 1 milliamp, I think it's about 17 times the voltage difference at the entrance. So it's a fixed and sort of linear slope that you can mess around with. But this has been a large turning point for me in how I'm going to implement voltage control. And you're going to see this in every circuit that I present to you onward. So my circuit design process is to find an initial circuit online for an application that I like, understand how it works, and then implement changes that I want to see done, or take out things that I don't find necessary, so that I've tailored it to my needs. And then I model it in a SPICE software, which is shown here. At the top is the sort of schematic that you can model in SPICE, and then at the bottom is an output from I'm totally blanking on the word. Simulation, that's the one. Output simulation. And so it's a very useful tool to understand and to implement changes to a circuit before you even build it, which is really wonderful. And then from there, I prototype it on a breadboard, see if it actually does what the SPICE software says it does, and then tinker with it from there, measure everything with all sorts of lab gear, and from there, design my own PCBs. So let's, I guess, talk briefly about this power supply that I had built last year. This follows the Eurorack sort of standard for power supplies. And I built it because I found that I got inconsistent results moving between different power supplies in different labs. And I didn't have a good means for testing my circuitry when I went home. I didn't have a power supply, so I had built this fixed power supply with plus minus 12 volts and a ground connection. And I had to be aware of how much current I'd probably be drawing from this, so I believe I went ahead and estimated about 1.25 amps for it, which is probably going to be fine for any application I'm going to throw at it. And then had to figure out safety concerns. Since I am generally less familiar with power electronics, I didn't want to stick my head in where it didn't belong and blow myself up. I had to worry about board connections and all that sort of jazz, so you can get the power between boards without having to solder wires into boards, which is not a really great idea. And so I pulled a lot from Eurorack for this. So this is the circuit that I based my circuit off of. This is from Erica Synths, which is a big Eurorack synth provider, and they've done a do-it-yourself sort of series with a man named Moritz Klein, who I'll mention again later, which is really great if you were looking to get into more basic electronics for sound design and synthesizers, so I'd recommend checking them out. And then I sort of harvested what I needed from that circuit to come up with this circuit, and since I'm less familiar with power electronics, I sort of cheated myself. I let myself cheat with this circuit and went for a black box IC that sort of takes in an input voltage and transforms it into the output voltages that I need. And so that's that large block in the middle of the circuit there. And I think that's the only real time that I've done that since, which is good for me, I guess. But unfortunately, it is only plus and minus 12 volts, which worked great when I was just doing analog circuits. But now that I'm implementing digital control circuits and need a 5-volt source or 3.3 volt source, I'm now using, or having to use, voltage regulators for that are a little bit less stable, a little bit more noisy, which isn't lovely. And so I might have to go back to the drawing board on this circuit and implement a digital voltage level source that I can pull from. But that will be for later. So this is the only circuit so far that I've done PCB design for. And so when you're designing PCBs, you have to think about how you're going to mount all your components. And so for me, for now, it's just through-hole components. You make a hole in the board that has a copper connection, you put the component through it, and you solder it in. It's simple and easy, but now it's very popular to make, and it's been popular for decades now, to make PCBs with surface mount devices, which are a lot smaller, but are a lot harder to solder, and they mount on the surface instead of through a hole. but I've been using through hole. You have to worry about the size of the board, how much space it's going to end up taking when you finally implement it in your case or whatever you're going to put it into, and how close you can get these components to each other. So for the power supply, that wasn't a terrible concern, but for analog sound generation circuitry, when you're running really high frequency information through these traces, you can only have them so close to each other before they bleed into each other, which is undesired. You have to worry about trace angles, which just as a general rule should be 45 degrees at maximum. Nothing to really worry about. And then I/O connectors, which I pulled from Eurorec, which use ribbon cables with 10 or 12 pin male-female connections, which I'll show you in just a minute. You have to worry about board mounting, and so I've put 4 holes in the corners of the board so I can put it wherever it has to go when it has to go there. And then your silk screen, which is just the writing on the PCB letting you know what is what and what goes where. So once I had an idea of what I wanted to do for all of that, I designed it in KiCad, which is a PCB modeling software. And so once I had done that and generated all the files and sent them off to a company, I had a product sent to me, which is pretty much exactly what I asked for. It was perfect for my work. So I had all the connections, which you can see have all these wires and legs that'll fit through these holes in the board. And I soldered them in to make this final product-ish PCB for myself for a voltage source. The cables that I'm using are, as I mentioned before, ribbon cables. And so you can see this big wine of ribbon cable that I bought, and these are right now 10-wire ribbon cables. So these are extremely, extremely thin wires that are inside of these, plastic rubber casings. And you can crimp these headers onto them that bite into the casing just enough to make contact with one specific wire. So it's a really easy and straightforward method of building cables and then implementing power design or power supplies. And so what's nice about this is that I can run a general bus wire using a handful of male connectors along one general run of cable, and then have small cables offshooting to individual PCBs depending on where I put the PCBs in the case. So now let's talk a bit about the oscillators that I've been working on. For the oscillators, I want each oscillator to have 3 general shapes: a sawtooth, a square wave, and a triangle wave. I'll show you pictures of those later. I want the square wave to have pulse width so you control how long the pulse is on or off. I would like to have a wave morphing, which I have been successful in implementing, which I'm very happy with. It lets me mix between the sawtooth and triangle waves while maintaining generally the same output voltage level. And then I mix that sum with the square wave. So instead of having one of 3 fixed waveforms to pick from, or even if you switch all of them on, they'll mix with each other in still a fixed manner. You can really manipulate it to whatever sound or whatever timbre you'd like before you even have to go on to mixing in other oscillators. And then I'd like to have a reversible saw for oscillator 3, since I'd like to eventually use oscillator 3 as a modulation source, which I'll talk about a bit later. And so I wanted the control scheme for these oscillators to be a Moog-style scheme where you have selections for octaves. So you'll have, 1 octave, an octave higher, an octave higher, an octave higher, and then from there you'll have coarse tunes. So you can sort of detune and do all sorts of wacky stuff between these oscillators. And then I wanted the third oscillator to have just an entirely coarse tune knob for its entire frequency range, so it's not reliant on these selection of octaves. And that again will play into it being a modulation source, which I'll mention later. And then I would also I will be implementing a switchable keyboard control for oscillator 3, again playing into the modulation source. And a master tuning for all of the oscillators, so if the whole system goes out of tune or anything like that, you can just turn the knob and it all gets where you want it to be. additional circuitry that I have implemented and or I'm working on implementing is a ring modulator between oscillators 2 and 3, which is a whole separate output and will be, a separate input in the mixer, which I'll show you later. And then hard sync for oscillator 2 to oscillator 1, which causes oscillator 2 to reset every time oscillator 1 does. And that can create some really interesting harmonic relationships between the two that I'll play in an audio sample for you. So the basis for my oscillator is Moritz Klein, here he is, his oscillator design. And it's a sawtooth core oscillator, which you can then take to manipulate into other shapes. And so this is an entirely, well, the frequency for this is voltage controlled, but the pulse width, for example, on this design is analog, so it's a knob, which I had to work around a little bit, but my design for this is a little bit more complex, where I've also added a triangle source, and then I've implemented OTAs to mix between the signals so I can have the wave morphing function that I wanted. And so this is just for a single oscillator, and so we'll have 3 of these plus other periphery on a PCB eventually. Here's a sort of the mess it ends up on a breadboard. And here are your basic wave shapes. So there is your sawtooth top left, triangle top right, square wave bottom left, and then square wave with some pulse width modulation on the bottom right. And let's briefly play you a sweep program that I designed to run through other controls. Oh, it's not playing on that screen. How interesting. There you are. Oh, I can't see it. So what you just heard there in order were its coarse tune feature, its fine tune feature, and then its solid triangle wave mixing feature, and then that sum being mixed with a square wave, which then had pulse width implemented on it. And every parameter that was just shown to you had a voltage control, so I could program it to be what it just was. So, as I mentioned earlier, I'd like to add a ring modulator. The ring modulator circuit that I took for my ring mod that I'll be implementing in my design is the Skull and Circuits circuit that you see here, which is a lot more complex than I need it to be because I'm providing it the 2 waves that it needs. So this circuit also implemented a sine wave generator, which I just don't need, so I took out. So here's my design. It's a lot more slimmed down, and so I just have inputs for carrier and modulator, and then your output at the end at the same sort of voltage level that the inputs came in at. So here's what ring modulator sort of looks like. So what you're seeing here is the blue wave is your input carrier, so it is the function that is, or it's the wave that is being operated on. Your yellow wave is your modulator, so it is modulating the blue wave, and the green wave is the output. So a ring modulator modulates the amplitude of the input wave by the level of the output wave. So you have the output being forced to follow the sort of amplitude of the modulator. So here's an example of how that sounds. And so, though it can create all sorts of odd and interesting harmonic behaviors like you just heard, it's also very, very useful for adding depth and body to harmonically tuned oscillators. So if you have your carrier and your modulator tuned to a harmonic relationship, it brings in a really nice undertone that thickens the body of the sound. So if you'd like to, you can get weird and whatever with it, but also it's just a really nice sound generation tool for harmonic sounds. Here was a relatively simple and brief circuit I threw together for hard sync between the oscillators, since the oscillators are based around Schmidt trigger inverters, which, in a very brief explanation, cause when the input senses that a voltage is passing below a threshold, it goes high, and when that input is passing above or into and above a separate higher threshold, it goes low. And so I took the output from one of the oscillators and generated a very brief pulse at a specific voltage that I wanted that would then cause the other Schmidt trigger inverter to re-trigger. An interesting issue that I ran into with this design is that when the frequencies of these two oscillators are extremely close to a harmonic relationship of each other, you get an interesting interaction between the reset of the Schmidt trigger inverter on the second oscillator and the first oscillator's prompt to reset the second. So you get a really not terrible sounding, but just unwanted harmonic output from that. So here's what that kind of looks like. So you have your oscillator 2 outputting green, and it is being forced to reset to the oscillator 1 every time the oscillator resets. I keep it. So in that example, you were not hearing the yellow wave at all. You were just hearing the green wave. And so that underlying constant tone that you're getting is caused by the wave being forced to reset to the frequency of oscillator 1. So it will always match the frequency of oscillator 1 while adding interesting harmonic, higher and higher harmonic information the higher you turn oscillator 2. But then you also heard the glitches that would happen every time it became closely harmonic interval with the oscillator 1. An idea that I'm having that I think would fix this, I just kind of didn't have time to get to this semester, would be to force the wave of oscillator 2 to reset to the middle of its cycle instead of to the top, and that way you're not getting, a double request for the Schmidt trigger inverter to re-trigger. And that way you're just resetting the wave at a fixed point every time. That isn't going to be problematic. So you're not getting any bounce from trying to push a low voltage. You're not getting any double triggering from a higher voltage. We'll see if that works. I don't know. We'll get there. Oh, it's still in the video. Sorry about that. Cool. So the majority of what I have to do with the oscillators is just, minor tweaking, making sure all the output voltages are where I want them, or if I think there are going to be some variations between each oscillator, then I'll implement just like a trim pot that you can use to, synchronize them before you put them away forever and never look at them again. I've got to fix that hard sync like I mentioned. If you looked really closely, you would see that the triangle has a little notch on the top where the tops don't quite meet each other. I'm not terribly worried about that. It sounds well enough like a triangle wave. It's not adding that much harmonic information, but if I ever get it in me to fix it, then I'll just go ahead and do it. I have an idea if I'm going to do that. And then I have to now start considering how I want to implement low-frequency oscillators for modulation purposes, which I will talk about later. So the mixer is, relatively basic. It's a mixer. So it takes in your oscillators, it takes in the ring modulator that the oscillators feed into. I would also like it to take in an external input that you can plug in from the outside, so you can run whatever you'd like out there to through your filter and your envelope generator and all the other effects that are at the end of that signal chain. And then I'd also like to implement a feedback or drive and or kind of situation where you take in either feedback from the end of the sound chain and put it into the mixer, so you boost the sound and start doing a little bit of clipping, or I would like to implement a drive that really starts clipping the circuits that follow and make the sound a little bit nastier. And so this is not something that I've breadboarded yet. For now, I'm just kind of using a non-inverting summing amplifier that's a fixed state, and that's good enough for me for now, but I'd intend to implement several OTAs, since those give me voltage controllable volume levels that are then sent through voltage controllable switches, the CD4066s, that are then buffered and amplified through this non-inverting summing amplifier. And so it should just be a relatively simple circuit. I don't imagine that it'll be anything terribly crazy. But what I have not given a whole ton of thought to yet is how I'm going to implement the amplification stage at the end to start things clipping and to start that sort of drive that I'll want to implement eventually through the circuits, the filter. I also have not implemented the external input, but again, I don't imagine that'll be crazy. Just set an expected value for input voltage levels, and if it surpasses that, just make sure it clips so it doesn't break anything. The filter, if you remember from last time, for those of you who were here, I had implemented a salad key style filter, which just did not give me very consistent responses, unfortunately. And part of that was the salad key filter design itself, and part of that was just that specific circuit. But between that and it not being totally voltage controllable, I just mixed it and decided to pursue a Moog ladder filter, which I know that I like, and which there is a relatively abundant amount of information for online. And so this filter includes resonance and self-oscillation once you push the resonance past a certain amount, which is very desirable to me. I also intend to implement keyboard tracking so that you have a range of a knob, say, and then you can change the cutoff of the filter depending on the note that you press on the keyboard. And so at its maximum keyboard tracking value, it would change the cutoff 1 octave per 1 octave played on the keyboard, and that lets you play all around the keyboard with this filter on without it cutting off harshly frequencies for higher frequency notes that it wouldn't cut off for lower frequency notes. And then, like I mentioned before, I'd like to implement saturation from the mixer into the filter, but that'll be at a later date. And so here is a general Moog ladder filter schematic. This was adapted from the memory Moog, which was Moog's big flagship in the 80s, Polysynth, which stores patches, all that stuff. And so I found a blogger online who does a lot of circuit work for synthesizers, and I appreciated how he approached his implementation of a Moog ladder. And so I based mine off of his, based off of the original. And so after, troubleshooting and fixing a couple of issues that were in his schematic, I was able to come up with a very functional Moog ladder filter that is completely voltage controllable. And on breadboard, it's, again, a big mess, but it does its job. So here are your filtered outputs. So I'm applying a square wave into the filter and giving it different levels of cutoff and resonance. So top left is just some cutoff with no resonance, so you can see it cuts off that sharp corner that is resultant of higher frequency information, which the filter is taking away. And then once you start implementing resonance, then you get these fluctuations in the output that are at the frequency of the filter's cutoff. So as you implement more and more resonance, the fluctuations get larger, and as you change the cutoff frequency, then you change the frequency of those fluctuations. And once you push the resonance past a certain point, you see at the bottom right, it totally self-oscillates and just becomes a giant sine wave. So here is a brief example. So a very nice feature of this particular oscillator circuit is that since it uses OTAs as much as it does, it has an OTA put. I was able to just kind of implement an OTA at the output, which lets me have a voltage-controlled amplifier instead of having to design a whole separate circuit for that. It's just one OTA that I've put at the end of that circuit. So still to do, again, just minor calibration and, again, implementing trim pots and little variable resistors for whatever I'd like to tweak once I end up putting on a PCB. But in addition to this filter, which already sounds really nice, I'd also like to have a second filter from the Korg MS-20, which is a little bit dirtier, has a little bit more attitude, is based on a Salad key filter. So again, it's not as consistent as what you just heard, but is a little bit raunchier in return, which I really enjoy. But what's nice about the MS-20 filter is that it is very easy to switch between low pass and high pass modes on that filter. So if I implement this filter in series with the Moog filter, I can have, a low pass and then a high pass, so I can carve out really whatever frequency ranges from these specific sounds that I want. And then if I implement envelope generators in the same way on these filters, then I can have bandpass effects, which is cut off of all information passed to band of frequencies that will move around once I implement that, which will sound really interesting. I just don't have now. What I do have is a schematic that I will end up using from Renee Schmidt, who was, again, a very well-respected member of the online DIY Eurorack community. Here is his schematic. Hey, those are OTAs. Funny how that keeps happening. And so, I totally forgot I have a video for that. So I have a video from the filter that I had built at this time last year, which will sound similar to this filter. So it's a dirtier, a little bit rougher, but it's a sound that I really enjoy. And so I will be implementing that filter in series after the Moog ladder filter. So now comes the envelope generator. These are the circuits that generate control voltages that will modulate these circuits that we've just been talking about. So for example, the filter cutoff or the amplifier level. These are often controlled by envelope generators, which take gate inputs, which is just an on and off from, say, for example, a key press on a keyboard, on and off. And so I wanted these to be logarithmic since we hear in a logarithmic scale, not a linear scale. Like I just mentioned, needed these to have gate control since that's how I plan to play this instrument. I wanted them to have inverting outputs, and I wanted them to have looping modes, which I'll show you very soon, are just really neat features that you don't see a whole ton of in a lot of synthesizers. And then I will have 3 of these total, most likely. 1 for the filter, 1 for the amplifier, and then 1 for modulation of whatever I choose to modulate with it. And these will all be implemented slightly differently, which I'll touch on in a moment. But this was tricky to find in a voltage controllable method. The circuit that I had built last year was lovely. It did what I needed it to do, but it, again, wasn't voltage controllable. I couldn't find a good way to make it voltage controllable, and so I had to go back to the drawing board, and I found this 80HSR circuit, as opposed to general 80SR attack, decay, sustain, release circuits. This also has a hold in the middle. I'll explain what all of that means to you when I have pictures of it in just a minute. But this sort of looked perfect to me because I couldn't find anything else that really worked for my use case. But unfortunately, this schematic that he uploaded to his website 25 to 30 years ago has an error in it that people have been trying to figure out for years. Like I found, X number of forum posts of people asking about it without answers. So I took it upon myself to try to fix it, and I was very successful in doing so, which I'm happy to say. So here's my circuit. It's essentially the same thing with that minor fix, but I've also implemented mixing between the inverting and non-inverting modes, which I'll show you in a second, and then a Schmidt trigger inverter from an op-amp to take feedback from the output for the looping mode. So when the output goes high, the inverter goes low and turns off the input. So then the output starts its decay phase. When the output goes low, the inverter goes high, turns on the input, and it starts the whole loop over again. So in that way, it's looping. Again, another jumbled breadboard mess, but it works. And so here is our what our envelope actually looks like. So in this case, for the top 2, the green is our input gate. So that is our on and off that is being fed to the circuit. And so you can see the phases of the circuit. First phase is attack, where it reaches its peak value and then decays, which is its second phase, to its sustain level. And that all happens as long as the gate is on. So if the gate turns off during any one of those phases, it immediately stops and moves to the decay phase, which is the end of the ADSR cycle. And then there is I don't know if you can see it very well, there is a brief hold implemented so that when the gate releases, it does not automatically or immediately proceed to its decay phase, or sorry, its release phase. And so that isn't a feature that I will be using a lot, but it is a feature that is very interesting in the looping mode, which is shown on the bottom here. On the left is just standard looping without the hold on, and so when you have implemented standard looping, it just does its attack phase until it reaches its highest point, then it goes to its release phase until it reaches its lowest point, and does that forever. But if you implement the hold, it holds the circuit once the Schmidt trigger inverter reads that high in and turns the input off. And so you get just a little bit of that decay and sustain phase in the loop, which is really powerful. I'm sort of glad this circuit has that. I never would have thought to do that ever. But here's an example of this being applied to the filter cutoff. So I'm able to control the level of the envelope with a control voltage. You can see in green. As it's stepping down, it goes from positive, smaller and smaller, and then increasingly more negative. So in this example, you'll hear it follow essentially this pattern, but once it starts going over into negative, the filter opens up so you can hear it coming down. Oh, that's not one. It's over here. So you have positive and negative contours for the filter cutoff provided by that envelope generator. And I feel that I should at least just briefly note, in the prior examples you only heard one oscillator operating. In this example you heard two that are summed 1 to 1, just for now with the non-inverting summing amplifier. And so the interesting phasing effect that you got there, that was due to a slight detune between the two oscillators, which is just a really very pleasant sound. And unfortunately, since it's all still living on the breadboard, it's not all too stable at the moment. But it's nice when it works. So what's still to do with this? Well, it's pretty well functional to what I wanted to do already, which is great. I do have to do calibration with the maximum and minimum times for each stage of the envelope. So for now, I haven't done a whole lot of that. I've just done enough of it to make sure it'll work within a range that I want. But what I intend to do is have for 0 to 10 volts input for each of those controls, say give it a range of, instantaneous to 15 seconds to reach the end of that stage before it moves on to the next. And then, like I said before, per application it'll have a slightly different implementation. So I don't know that I would want to have, for example, the inverting effect that you just heard operate on the amplifier. Maybe I will. It's could be interesting, but it's just not something that you hear often. And then what I'm considering doing, which what I think could be really very interesting, is having an additional hold stage when the attack finishes. So instead of immediately going to its decay and sustain after you reach that peak attack value, it'll hold there for just a minute, which could be pretty neat. And then again, another sort of hold, a delay stage between when you provide your gate and when the attack actually starts. But I admittedly don't have a great idea of how I'm going to do either of those for now. So we'll see, but for now it really does what I want it to do, which I'm happy with. And so what do I still have to do from the analog side? What I haven't implemented yet that is really important to me is a glide or portamento feature, which allows you to, instead of instantaneously switching between two notes when you press two notes, it sort of slides between them. And so as you turn up the glide or portamento, it takes longer to get between each note, which is a really neat sound, and I think is part, to me, of the identity of the monosynth, and even just synthesizers in general. So that's something that I'll be implementing soon, and that can be something as simple as an RC circuit between, or put after the control voltage. So instead of having this, immediate switch, it takes a little while for that capacitor to fill and gives you that glide effect. I need to figure out what I'm doing for modulation, which I know I haven't explained a whole lot to you about yet. So what modulation is a set of waveforms or voltage functions that you can assign freely to multiple parameters across your synthesizer. So for example, if you took a low frequency oscillator, which instead of looping or oscillating at audio frequencies operates, once per second or twice per second, much slower, but much more, at a perceptible rate to people. If you provide that to, say, the filter cutoff, you get this just kind of really nice on and on opening and closing sound. So that's an example of modulation. And so what I'd like to, at the very least, have for modulation is a low frequency oscillator, which I intend to make a digitally controlled oscillator instead of the voltage controlled oscillators, which I showed you earlier. And the plus side of that would be that I can sync it to a clock. So for example, if I take a MIDI clock in that has a particular tempo, I can say, okay, I want this to oscillate at 4 times per beat or 2 times per beat, that kind of thing. So instead of just kind of goofing around with it until you get something that sort of works, you have exactly the frequency that you want there. And that can be, controlled probably pretty easily, honestly, from the digital control circuits, which I've implemented, which I'll talk about soon. And then I'll have a modulation envelope, so just like the envelope generator I showed you a second ago. A sample and hold circuit, which is just like a random value generator. And maybe some more if I feel like getting crazy, but those are really the majority of what I want to implement in modulation. So what I still have to figure out from that front is how I'm going to implement that DCO and how I'm going to go about mixing all of these together before sending them off to where they're going to go. And additionally, I guess, now that I've made it a point to make everything voltage controllable, I can send that modulation anywhere, which is great, but I also have to now figure out where I want to put it. So now I'd also like to have some effect at the end of the signal chain, so that being wave folding or distortion. Wave folding is really interesting. If you're not familiar, I wouldn't be surprised if you weren't. Wave folding is an effect that once your input reaches a threshold value, it starts folding on that value, so it inverts at that threshold. So say you have a triangle input that you're going to fold. Once it reaches your upper threshold, it will invert for the rest of its wave, and then it'll come back up and then finish its regular triangle. And so that is a really interesting sound, but isn't totally interesting on its own when applying just to oscillators, because oscillators, as you saw from my example before, are already pointy and full of high-frequency information. So what I'm thinking about doing is placing that wave folder after the filter once everything's all rounded off, and then that'll invoke a lot of pointed corners and high-frequency information, but also will have the double effect of providing a total ceiling for that wave, which is almost like distortion clipping, where it reaches its peak and then can't go any further, and you get a distorted sound out of that. So it's a very interesting variation on distortion that I can implement then. I'd like to implement just sort of a standard chorus. I like the sound of the Juno choruses, if any of you are familiar. And then bucket brigade delay reverb, which is interesting, where it passes the signal along a chain of capacitors until you have a time-delayed result at the end of that chain. And so there are X number of ways to implement that. I'll have to figure that out later. And then maybe reverb, but reverb would have to be a digital process unless I decide to put a spring reverb into the unit, which I doubt I will. And then a bit crusher, which is also relatively interesting and is also not very hard to implement. So that would be very much similar to the sample and hold that I would be putting on the modulation, where it takes a sample of the wave that is being fed every time an oscillator or its control is looped. And in that way, it is reducing the effective bit rate or sample rate of that sound. And it's a really neat effect. And then I have to finally implement master volume, patch volume, and a headphone amplifier, which, again, should not be hard. They're just different configurations for getting the audio out from the unit. So now on to what I've really been spending a lot of time with this semester is the digital controls front of the synthesizer. So since I was able to make all of my analog circuitry voltage controllable, I now had to come up with a system that could very quickly and very accurately deliver these control voltages to the circuits. And so the tasks for the digital control system that I have laid out thus far are processing control voltages as digital values. So that means you're taking control voltages from a panel and you're storing them as digital data in a processor, which is then going to be spat out to the analog circuitry. And that information will have to update in real time as necessary. So say you load a preset, but then you tweak a knob, that knob tweak should be reflected in the sound that you're hearing. You'll have to convert the digital data to control voltage outputs, which is possible through a digital to analog converter, which I'll show you in a short moment. And then you have to be able to store data for recall at a later time, which again isn't terribly hard once you have that data as digital data. Additionally, the digital control system should be able to process MIDI messages. So it should read MIDI coming in, it should parse what it is, and then convert those input messages into control voltages for, say, the oscillator pitch and the envelope gate. And then should also be sending MIDI messages out depending on the notes that it is getting, if you want to put something, or if you want to send any MIDI information to a throughput, or if you've implemented a clock or a tempo inside the system, it should spit out that information on an output. And so the main concerns for a digital control system are speed, so you don't want it to lag behind at all. So when you turn a knob, it should sound instantaneous, like there's, nothing between that knob and that analog circuit, even though there is a whole bunch of stuff there. And then you also have to be very, very considerate about noise and all that, because that can very extremely affect and very noticeably affect an audio circuit. And then additionally, you have to give consideration to the levels of your control voltages. So what is your system able to spit out? And then what can your circuits take from that system? And how can you match them together to make sure you're getting the total range of application for each circuit? So the processing method that I've decided to use is based on one that has been used for probably the better part of 50 years in analog circuits, and analog synthesizers, where it reads the control values from a control board in front of you. So you turn a knob, it changes the voltage controls, and it spits out a voltage into a multiplexer, which is like a digital switch. And so it'll switch each individual control value from a knob or a switch, what have you, into an analog to digital converter at extremely high speeds, so it seems instantaneous to the user. And once it's done that, it will communicate that to a microcontroller in whatever communication protocol that ADC is capable of. My choice for this project is SPI, since it is probably the fastest communication protocol there is that is still reliable. And then that microcontroller, once it has that data, has to in turn give that data sequentially to a digital to analog converter. So it is in order saying, okay, this control voltage 1, 2, 3, 4, 5, and then that is being sent to multiplexers, which are going to switch those to individual 1, 2, 3, 4, 5 outputs, and hold on to those voltage values so that the analog circuits are getting constant values. And so the tools that I've chosen to implement this with are the Raspberry Pi Pico 2 for my microcontroller, and I've chosen that because it's extremely fast, powerful, and inexpensive. It has multiple cores, which is great, which means I can run 2 different pieces of code immediately at the same time. So one in this case would be the control voltage processing, and then the other would be MIDI processing at the same time. It programs in C and C++, which I am proficient in is also a very fast programming language to run. And then it also includes peripherals for SPI, UART, and I2C communication protocols for whatever digital devices I will end up using in conjunction with Pico. The DAC that I've chosen is the 805676. And so this takes SPI up to 50 megahertz, so ripping fast. And it also has 8 DACs on it, so if I would like to, I can have 8 individual DAC outputs at the same time. And then for multiplexers, I've chosen the CD4051 from Texas Instruments, just because it's kind of standard and fast enough for what I needed to do. And I have not yet begun to implement the input multiplexers or the analog to digital converters. So right now, I've just been focusing on defining digital values in my programs and then taking those values, converting them with the DAC, and sending that to multiplexers, which then gets sent out to the circuits. And so, I guess a quick aside, the DAC that I chose was only available in surface mount packages. So I had to learn how to solder surface mount devices. So this was my first surface mount soldering experience, and it's went well enough. I blew up one, which is okay for your first time, but the second one is working, which is the important part. And so here's an example of what an SPI signal looks like between the Pico and the DAC. So the information that I'm feeding it comes sort of in 3 parts. So the blue signal that you see is the chip select signal, and that is a normal high. So if that signal is high, the chip does not try to read anything. It just sits there and does nothing. And once that voltage goes low, then it realizes that it has to start reading something. The green signal that you're seeing there is the clock signal. And so this allows the devices to synchronize their send and receives for data. And the yellow signal there is the data out from the Pico to the SPI, which this specific DAC reads on the falling edges of the clock. And so I've provided you a translation to binary in red on the bottom there, the message that the Pico is providing to the DAC. And this is based on the data sheet and how this specific DAC works. So for example, those first 4 bits tell the DAC to update an input register. The next 4 bits, so that's 0001 means update input register. The next 4 bits, all zeros, mean that I will be updating specifically the register for DAC 0. And then the rest of the 16 bits are information about the voltage that it will be spitting out. So this translates to setting the DAC channel 0 input register to 0.866 volts. And so once this transmission is done, the chip select goes back up and the DAC stops reading. I would also like to call attention to the resolution at the top of the screen. You probably can't read it from there, I don't blame you, it's small, but it says 168 nanoseconds per resolution, which is the amount of time, the horizontal time per block that you see on the readout. And so this specific example was taken operating the SPI at 25 megahertz. So this is extremely fast data transfer, and that way, the faster I can run it out, the faster it gets to where it's going, the less latency you have between your controls and the sound you'll hear. Is this is not a video? Okay. No, it's not. Okay, cool. So once it leaves the DAC, it's in a sequential order. So you have control voltage 1, 2, 3, 4, 5 that have to be split out to all these different channels. And so this is where our multiplexers come in. And these multiplexers each feed to sample and hold circuits, which are the op-amps and capacitors that you see implemented multiple times here. So each multiplexer output sends to a sample and hold. So if you switch control voltage 1 through channel 1 from the multiplexer, and then turn the multiplexer off, switch to channel 2, that channel 1 voltage is held by the sample and hold voltage and is output at that voltage for probably 6 milliseconds before it starts leaking. So you have to be running this thing very, very quickly to keep refreshing these sample and holds. But you have sample and holds implemented for every single control voltage that you have to implement for your circuits to work. And so you might notice that I did not put a sample and hold on the last output of the multiplexer. I'll show you an error that I ran into and why I decided to do it this way. So when I was initially getting this control system up and running, I found that there was a lot of noise coming through the circuit, and you could maybe see it, maybe. I tried to circle the noise blips in the signal there. But this noise was caused by each sample and hold reading a little bit of the previous sample and hold's value on the output. And it looks pretty ugly. It looks, where do I have my mouse? So you can see small peaks from this specific output reading from the previous. And that affects it whenever there are different voltage values, which will be probably most of the time. And that causes a lot of noise to get through into your signal. And so what I found the cause of this issue was that multiplexers have an internal capacitance. And so even if you turn the multiplexer completely off and leave it off for a decent while, it will hold on to that previous voltage that was fed to whichever channel it was last, fed. And so what was happening was that this voltage was being held over from the previous channel into the new channel and was pretty immediately discharging to the proper value that I was feeding it, which caused those noise spikes. So what I decided to try to do to get around this was to feed control voltage to one channel, then turn off the DAC, switch it to the last channel, which I just put a resistor to ground on, and try to discharge that held voltage, and then set that to the next voltage before switching it to the actual desired next output. And though that worked for what I wanted it to do, I also found that it put a strange loading effect on the DAC output, since it was starting to pull decent amounts of current when you wanted to discharge that held value quickly. So what I found interestingly worked was just removing that resistor and switching it to that open channel, feeding it that new voltage, and then switching it to the proper output channel. Solved the problem. And so now the sequential output from your DAC will look like a bunch of different voltage values. And then I also plugged in maybe 100 cycles of dummy values, so that's why there's that much blank space there, to simulate what my cycle time would be if I had, 110, 115 different control voltages. And again, you probably can't see the resolution, but this cycle repeats once every 2 milliseconds, which is pretty fast. And I believe that this specific screenshot was taken before I started operating at the high SPI speed that I am now. So I believe it is a bit faster. But on top of this, this is just one DAC output, which is feeding all of the multiplexers. So it has to feed all the individual control voltages in series. But if I decide to split them up along all 8 of my available DAC outputs, I could have, number of control voltages divided by 8 running out of these 8 all the time. So I've effectively cut my cycle time down, or divided my cycle count time by 8. So a closer look at what the signals will look like from your DAC are shown here. So the yellow signals are the sequential control voltages, and the green signal is one specific sample and hold for the filter cutoff voltage. So it follows very well, and then you can see it doesn't, droop or drain before getting re-upped by the DAC output. And so though you're only seeing one sample and hold here, each individual voltage level has its own sample and hold. So like I mentioned before, what I still would like to do is start running these, multiple DACs on this one chip in parallel so I don't have to run every single control parameter in series. And that can be done very nicely since this specific DAC lets me update all of the input registers for all of these specific or individual converters with their next level and then update them all at the same time, which is nice. I still have to do the ADC input voltage system from, analog voltages through the ADC to the pico. I imagine that the process will be relatively similar, and like I did with the, digital outputs system, I'm sure I'll run into a couple bugs, but nothing that I can't fix. The main concerns for me with the ADC are sampling time. Since I haven't done a whole lot of research on ADCs, but it seems like the sampling time for ADCs is generally slower than DAC output settling times. So the DAC can often spit out voltages consistently faster than the ADC can sample them. So the speed that I just showed you would probably be, or the cycle time I just showed you would probably be multiplied by 2 or 3 times, depending on how long the ADCs take to multiplex in and read all these individual control voltages, which is why running DAC outputs in parallel would be very nice. I do have to come up with this front panel design once I've finished designing all these analog circuits and know what I have to control. And then preset saving, which is something I could realistically do now. The Pico has flash memory on it, which I could just start storing an array of data values to if I wanted to. I'm also considering an off-board EEPROM, which is an off-board, read-only memory, which you can write to overwrite previous values. But this is not that crazy an issue, and it's something that I can realistically just do now. So the second part of the digital side is your MIDI processing. And so that is, input and output messages using this protocol. MIDI is a UART protocol. It uses the Universal Asynchronous Receiver Transmitter Protocol at a baud or cycle rate of about 31,000 cycles a second, which is very fast, but considerably slower than the SPI that I was running, which was 25 megahertz. So I did not want to have to run these serially, so I didn't want to have the MIDI processing, reading a MIDI signal or sending a MIDI signal, take up time on the processor that was running the SPI to the DAC. So this is where I started to implement multi-core design and threading on the Pico so I could have the first core doing all the control voltage processing, second core doing all the MIDI processing. And these allow me to do these simultaneously without interfering with each other, unless I tell them to. And so, likewise to wanting to run the control voltages and the MIDI at the same time, I'd also like to run MIDI in and out at the same time. But if I'm running MIDI on one processor, that becomes a little bit harder. So what I also decided to do was implement interrupts on the MIDI input, which tell me if the input buffer on the Pico has a byte of data to read, and that input or that interrupt tells me, okay, there's an available byte of data. I program that interrupt to take that data, put it in a queue, and then return right to where the program was before it did that. And then I also established a background asynchronous context, which is a bit higher level computer science term, which allows you to establish a worker that will do work in the background of a general program that you're running at the same time on that same core. And so it doesn't necessarily do it at the same time as you would one core, 2 cores that can do separate things at the same time. What it does instead is switches at extremely high rates between doing these 2 tasks. So it seems like they're being done concurrently with, about as little added operation time for either of the 2 operations as possible. And I've been successful in implementing both of those, which I'm very, very happy to say, since if it didn't work, I probably would have just thrown it out and did something else. And then I have to take the MIDI data that I've just read from an input and send that to the first core for processing for control voltages and gates for the analog circuitry. So MIDI receives UART messages which look like this, and these are just raw zeros and ones. And the way that UART works is that you set the communicating devices to the same baud rate, so they communicate at the same frequency. And then UART uses start and stop bits between each byte send to indicate that a communication is starting and ending. So it's a lot simpler than SPI, but it is a lot more generally applicable to a lot of controllers. So there are a couple interesting quirks about UART, like I just said, one being the stop and start commands, or stop and start bits. So you can see them indicated on this diagram as down arrows and up arrows. Down arrow is the start of a new message. Up arrow is the end of that message. So you've communicated one byte in that time. And then a new down arrow for a new byte. A new up arrow to indicate that you've communicated that byte completely. And then in case of any data loss, UART communicates the least significant figure first. So when looking at UART on a screen, you have to read from right to left instead of left to right like you'd usually be used to. So once a UART message is finished, you have that up arrow, you read from right to left to get the actual value. So this specific UART for MIDI comes to the hex code that is indicated at the bottom of the screen there, and that first hex code 9 indicates a note on message. The hex code following in 0 indicates that it's on the channel 0. So that is a complete byte. That is what's called a status byte. It tells you what's going on. So you have a note on channel 0, and then for this specific status byte, you know you will have 2 data bytes. I've shown one here. So the first data byte tells you the note. So hex code 3C translates to note number 60 or C4 on musical scale, and then this note on also includes a note velocity byte, which is not shown here. So still to do about MIDI is comprehensive general implementation. Since I couldn't find a MIDI library that would work very cohesively with how I'm setting things up, I've decided to just process it myself, which is worked fine. I'm getting the note values and gates and tempos that I need from the incoming device, but it is hardly comprehensive. And then I still haven't implemented MIDI out. I've just set things up in a manner that I can start implementing MIDI out when I have the bandwidth to. So let's take a little look at a couple of testing setups that I've had for this project. On the left, you can see at my desk at home, I'm using the power supply PCB, which I designed to suss out new stuff. And then setups in labs would often look like this, where I set up the circuit, I set up an audio interface for recording audio output from the circuit, run that into my computer. The computer is often hosting a code compiler, so I can write new code, update that, compile it, send it to the Pico to do something different. And then I'm also using power supplies and scopes to measure whatever I need to measure at any given point in time. So currently the circuit looks like this. I've just bumped up a bunch of breadboards. So the bottom breadboard on that that group of 3 is an oscillator. The board up above it has a wave folder on it that is kind of working. So since it's not totally working, I did not take any audio samples of it. To the right of that wave folder are a bunch of current sources that convert control voltages to currents for OTAs. The board above that is the multiplexer circuit board, which takes the DAC output voltages and splits it out to a bunch of individual voltages, which you can see I'm passing around through this spaghetti of wires everywhere. The circuit to the right is the filter modulator. The top right circuit is the envelope generator. The top left circuit is the Pico control board with the DAC on its right and also a MIDI connector implemented on it. And then the leftmost board is a second very, very basic oscillator core so I could have the sound of 2 oscillators running. The power draw that is resulting from this set of breadboards is pretty good for now. Considering that I've not implemented a lot of stuff, this is hardly indicative of the final power draw of the whole system, but I'm not drawing in 2 watts on either the positive 12 volts or the negative 12 volts, which are the middle and right supplies that you see there, which is good since my power supply that I built for myself is rated for up to 25 watts. I have plenty of headroom to implement more circuits moving forward. So now considerations to be made when moving from a monophonic synthesizer to a polyphonic synthesizer. You have to, upscale it by the number of times as you want voices. So if you want 5 voices, 10 voices, you have to have 5 or 10 times the number of the analog circuits that you made for one voice. So since I want to have, all these, voices and configurations, not only do I have to build all these more circuits and, spend the money on that and figure out where I'm going to put all these, PCBs and all that, I also have to program all these different configurations once I have a polyphonic, receptacle for polyphonic program controls. And so I, like I mentioned before, bitemporality split and layered is a feature that I would like to implement. I have to program that. Monophonic mode, which would be really interesting, lets you just run the polyphonic synthesizer as a monophonic synthesizer. And then unison mode, which is really nice, lets you run it as a monosynth, but you layer each of the individual polyphonic voices on top of each other to get a really wide and thick sound. But like I said, I have to figure out how I'm going to program each of those when that time comes. I also have to worry about new control processes. So I have to now worry about the uptick of MIDI messages I take in for, voice count. Now I have, instead of just handling one voice at a time, I have to keep track of 5 or 10, and how I'm going to reassign each of these voices when a new note is pressed, or when I let go of a different note, or things like that. And then control processes for multiple voices, I will have to, again, increase the number of control voltages, but also worry about which control parameters can I send to each voice that will be the same and which parameters will have to be different. So for example, the same filter cutoff to all these voices, but then different pitch controls to all these voices I'll have to start worrying about. And then, like I mentioned before, you have to multiply the quantity and price of the components that you're going to have to buy to use for making a polyphonic synthesizer. And so, of course, that comes with cost and complexity of circuit design, but that also comes with size. So now you have to start worrying about, okay, how big can my PCBs be? How heavy can I make this thing? How big and bulky can this synthesizer be before I can't take it anywhere and it becomes a piece of furniture in my house, which is undesirable. And so a process that a lot of synth manufacturers have come to use in the last several decades is developing voice cards, which are compact individual cards for a voice that include all the circuits for one voice, and you make as many of them as you need voices. And then you have a master control board which will receive X number of these voice cards. And so when I end up making this into a polysynth, I expect that I will be developing voice cards and also using specialized ICs, which I've been avoiding for now for the sake of learning. Once I have to consider space as a limiting factor, I will have to scale down these circuits and use ICs that are a lot smaller that do effectively the same things as my circuits currently do in a smaller package. Unfortunately, though these are a lot smaller and a lot more useful and very easy to implement because you don't have to worry about each individual component, you do have to worry about costs and quantity. These specialized ICs can be extremely expensive. I believe I checked last year, so I don't know what the current market looks like with new tariffs and all of this kind of stuff, but as of my last presentation, buying 30 oscillator chips came up to several $100s, which is not cool, you know? When I could, of course, buy the raw components for a fraction of that, but then take up more space. So that'll be a, struggle I have with myself for that. And it's shown here as a very, very compact and well thought out voice card, which implements a very interesting method of installation, which is PCIe, which you see a lot in computers for installing, it's like sticks of RAM. You establish contact pads on one end of your PCB, which will slot into a slot on your master control board, and then provide your connections that way. So you're not running, X number of cables between X number of boards and having a big old mess inside of your machine. So that's enough talking. Now I can actually play the synthesizer for you guys. I've got it set up here on the table. You can't see it, but once I'm done, yapping at you, you're more than welcome to come up here and take a look at what I've got going. And I'd like to, before anything else, say that I am controlling this using my synthesizer, but the audio that you're hearing is not coming from the synthesizer. That is just being a MIDI provider, so that is providing MIDI messages alone to my circuitry, which then on its own processes everything and sends out control voltages and generates the audio that you're going to hear now. So I'm going to give it just a second to warm up and let everything, get into before I start playing around with it. Let's get there. So I'm very pleased to say that it is very immediately receptive to new note presses as immediate as I can tell. I was also able to successfully implement a feature of monophonic synthesizers that only allows you to play one note at a time, but still processes all the notes that you've pressed at once. So it essentially takes all these notes, saves them in the order that you've pressed them, sticks them in a list, and then removes notes as you let them go. So if you press 6 notes, it plays the top voice, you let go of the middle voice. You wouldn't hear that happened, but once you start letting go of other voices, that voice is also gone. So I'll give you an example of that right now. So I'm now playing a 4-note chord. You're only hearing one note, and now I'm going to sequentially release the notes that you hear. And I can do that with, however many I want. And since it's, receptive to MIDI overall, it's receptive to, of course, keyboard control, but also sequences. And again, it's instantaneous as far as I can tell, so once I crank this up to an extremely high tempo, it will track that extremely well. Now, for my next trick. In front of your very eyes and ears, I will, in real time, update control voltages in a program, which I will then load onto the Pico, and you will hear that change implemented on the Pico without my having to touch the circuits at all. So right now I've got it set to oscillator 1 is a sawtooth-ish. Let's make it a triangle. So we've got, coarse tune, fine tune, solid triangle, say it's a triangle. And then it's got a little bit of square mixed in. Let's say we want even less. And let's say we want even more of an extreme pulse width. Cutoff is fine enough where it is, but let's say we want to hear a little bit more of our general frequencies, and then let's take the resonance down a little bit. And now let's change our envelope value. So since I've changed the cutoff amount, I'm going to reduce the envelope amount to, say, 2.5. I'm going to change the attack time to make it pretty instant. I'm going to, again, do the same for decay. That was fine what it was. Going to bring the sustain value up, and then give it a shorter release. Now let's compile that. Lost my power cable. Flash that over to Pico. And now that I've done that, I can plug it right back in and you'll hear a different sort of sound. Or you should. Huh. Alright, that took a wrong turn. What happened? Well, I'm sorry about that, guys. I don't know why it's not working now. That's kind of ridiculous. Huh. Wonder if I change something back if it'll start making sound again. Well, guess that's a problem for me to figure out now. I'm sorry about that, guys. Well, you heard it working. At least you know about that. Shame it didn't update like I hoped it would, but I guess that's a couple more bugs for me to work out where it goes. I think that generally concludes what I've got to say to y'all. Any questions? Yeah.
I missed the beginning of it, so I apologize if you answered it.
You're totally good.
Is there a reason why you're trying to do this on the analog side instead of doing it completely digitally?
Just because I like the sound of it.
Okay.
I don't totally love digital, and even though digital emulations of analog have gotten extremely good, it's still not quite there to me.
Okay.
And so, and even beyond that, this is just a great way for me to, beyond getting a synthesizer, to learn about electronics, which is something that I can apply to anywhere in the job industry or even just in hobbies and spare time. So, there you go. Thanks for asking the question.
Thank you.
Anybody else?
I have one more.
Go ahead.
I've done a decent amount with the digital side, but I'm an electrical engineer and I'm trying to get a little bit more into the analog side and use what I've been learning. How would you suggest getting into this? Is there a good first project, someone I can learn from on YouTube or something?
Yes, as a matter of fact. I mentioned a lot earlier in the presentation, his name is Moritz Klein, Moritz-Klein, and he has a pretty good series of videos about the very basics of analog synthesizers and the electronic theory that goes on behind making them work. And so that's sort of where I started, X number of years ago, or just probably close to 2 years ago now. I started watching his videos, and then through the audio degree, took a lot of electronics courses, which of course elevated my understanding of electronics to the level where it is now. But if you're looking for a beginner's place, for sound design especially, there it is.
Thank you.
Yeah.
Have you looked at drum machines?
I've been kicking around the idea of drum machines. I've never owned one. I've just played around with them before, so what I'd really like to do is just get one and own one before I try to go around building one. But, I don't know, that falls into the, 3 a.m. kicking around dumb ideas in my head, like, okay, do I build a drum machine into a synthesizer and make this a joint deal, or like, and that could be a project years down the road, but even then, so yes, I'm also considering that sort of, circuit design for drum sounds, but not yet. Yes?
When you fire up your synthesizer and you let it warm up, you kind of heard like the beat notes.
Mm-hmm.
To me, that sounds like two oscillators in your system that are unintentionally mixing, and often like that oscillator frequency is really dependent on like the temperature of your situation with your oscillator. Are you temperature control your oscillators? Have you thought
Yes.
about that? Like, what's that look like in your time?
It's not anything extremely complex, but I have implemented a handful of thermistors throughout these circuits to make sure that everything is stable enough.
Yeah.
So,
What's stable enough to you?
sounds good. It's not a scientific term, at least not yet. But so my considerations for temperature regulation are including temperature dependent resistant components like thermistors, but also will include placing temperature dependent components like transistors as closely together as possible on a PCB once that finally gets going. So I haven't given a whole ton of consideration. It's just enough to not sound terrible.
Yeah. How long does it usually take? Because it sounds like it's self-heating, so it hits a steady state, and that's probably when
Yes.
you get it balanced.
Yes.
How long does it usually take to hit steady state when you turn it on?
It sort of depends, but it's also hard to say with breadboarding for now, but really not that long. I'd say give it 30 seconds to warm up, and that's good.
Okay. Thank you.
Yeah.
It's just so many fun problems to chase down, and they're not even problems. Creative and really fun probably to hear your sound.
Yeah, thank you. Anybody else? All right, well then I'd like to say a few quick thank yous first to Dr. Freeborn. Thank you for your help in all your advice and information in implementing the digital control side that I've been, fighting with myself and Circuits so hard on. I'd also like to say thank you to Dr. Nishani, who does similar sort of mixed signal work to this kind of application, who also sheds some light on the digital side. I'd like to thank Dr. Taylor for his advice on PCB design, who took time out of his day to sort of initiate me and then point me in a better direction than I was headed. And also to Dr. Taylor and Dr. Ricks together for giving me access to a lab on campus. I wouldn't have been able to do a lot of this if I didn't have that. And that's all that I've got for you. Thank you guys for coming. An hour 45. I'm so sorry. Well, thank you for sticking around. I didn't realize that was the case.